So we're going to be looking at absolute value functions. So this is the parent function, y equals the absolute value of x. This is where all the absolute value graphs stem from, and we're always going to default to this function first. So this is a piecewise function. X is greater than 0, we have the line y equals x. When x is less than or equal to 0, we have the line y equals negative x. So this is a piecewise function. And you can see if you plug in 0 into the original equation, you're going to get absolute value of 0, which is 0. That's the coordinate for our vertex. If you plug in negative 1, you're going to get the absolute value of negative 1, which is positive 1, so negative 1, 1. Plug in negative 2, the absolute value of negative 2 is positive 2. And then when you start plugging in positive values, you always get that positive value back. So you can see that we go up by a slope of 1 on the right and up by a slope of negative 1 on the left. Every absolute value function has an axis of symmetry. So it's an axis that creates symmetry in the graph. So if you notice here, if I'm on my axis of symmetry and I go left 1 unit, that means I'm going to go right 1 unit to get to my graph. Same thing, there's always symmetry from the left and symmetry from the right. And this continues for the entire graph. So for our parent function, our vertex is always 0, 0. Our axis of symmetry is always x equals 0, the y-axis. The domain for the parent function will always be all real numbers. And the range for the parent function is y greater than or equal to 0. Now when we start shifting this function around the coordinate plane, all of this will change. But for the parent function, this will always be true. The vertex is 0, 0, the axis of symmetry is x equals 0, and our domain is all reals, and our range will always be y greater than or equal to 0. When the absolute value function starts shifting away from its parent function, we have to look at the general form of the absolute value function. So the number outside of the absolute value bars is a. If a is bigger than 1, then that's a stretch. We're going to get more narrow. If a is between 0 and 1, we're going to get wider, and that's a compression. We're pressing it down. If you happen to see a negative sign, that is neither a stretch or compression. That is a reflection over the x-axis. Now on the inside here, inside the absolute value bars, we have our h, and h is going to shift us left or right. If you look at the equation and see a negative sign, then h is positive and we're shifting to the right. And if you see a plus, then h is negative and it's a left shift. Now on the outside of the absolute value bars, we have our k. K is going to shift us up or down. If it's up, we're going to see a plus. If it's down, we're going to see a minus. Our vertex from the parent function is going to move. It's going to be hk, where h is the horizontal translation and k is the vertical shift. The axis of symmetry will not change unless you move left or right. So if h changes, then the axis of symmetry will also change. So let's graph this function, y equals the absolute value of x plus 5. So I'm going to take my parent function and I'm going to shift all the points up 5 units. So graphing your parent function points, we are going to shift all of them up 5 units, which means my vertex shifts from 0, 0 to 0, 5. Notice how because there's no value in front of x, that the slope stays positive 1 to the right and negative 1 to the left. You want to, of course, label a few additional points. Label your axes. So our vertex, our new vertex, is 0, 5, and I could have gotten that straight from the equation. H is 0, k is 5. Our axis of symmetry is going to stay x equals 0. So remember, it stays x equals 0 as long as there is no horizontal shift. And that's it. The domain would stay all real numbers. And the range is going to start at the y coordinate of the vertex and go up. So here I'm going to have a horizontal shift because I'm inside the absolute value bars right next to my x. I see a plus 7, so I want to recall my general form. And I know that I'm supposed to have a minus h. So if I don't see the minus there, that actually means that h is negative 7. And I'm going to go to the left 7, to the negative direction 7. So I plot my parent function. And then I'm going to shift all of these points to the left 7 units. Still keeping that positive 1 slope to the right of the vertex and negative 1 slope to the left of the vertex. And that's only because there's no numbers in front of the x. So connecting my dots. My vertex now, h is negative 7, so it's negative 7, 0. Plot a few additional points. We're going to get negative 6, 1, negative 8, 1. And label my axes. And of course, we have to do axis of symmetry. So your axis of symmetry goes right through the vertex. Since my vertex had a horizontal shift, then that means my axis of symmetry will move with it. So it's going to be x equals negative 7. The domain is also going to stay all reals, all real numbers. And the range is always y greater than or equal to, because we're open up to k, so we're going to have greater than or equal to 0. So for this function, I have two different translations going on. I'm going to shift all of the coordinates to the left 3. So h is negative 3. And I'm going to shift all the coordinates down 6 because k is negative 6. So plotting my parent function points. All of these points need to shift left 3 and down 6. So whether you do both of these shifts in one motion or you do them separately, that's up to you, and it doesn't matter which you do first. So our vertex moved from 0, 0 to being hk, so negative 3, negative 6. Since I had a horizontal transformation, that means that I'm going to also move my axis of symmetry. So my axis of symmetry is going to be x equals h. So my AOS is going to be x equals negative 3. And there we go. So it doesn't matter if you do both shifts at the same time or if you want to do them individually. The domain stays all real numbers. And the range is going to start at the y coordinate of the vertex, and because we're faced up, it's going to go up. So I have two different things going on here. I have a reflection over the x-axis as well as a vertical shift. So I need to reflect over the x-axis. And k is going to be 2, so I need to shift up 2. Now, unlike before where I had a horizontal and a vertical shift, whenever you're reflecting, you must reflect first before you start shifting left, right, up, or down. Now, this is because we actually are going to reflect over the vertex, but when the vertex is 0, 0, we can use the x-axis to help us. So once we move from the vertex being 0, 0, reflecting gets more difficult. So we are going to reflect first. So plot your parent function points. And then we are going to reflect them over the x-axis. So here's the x-axis. Reflecting means if your distance is 1 away, then we go 1 away the other way over the axis. This guy is 2 away, so we're going to go 2 away down. 3 away, and so forth. Now the vertex is not going to move because it's actually on the axis. Now I need to take all of these points and shift them up 2 for my k being 2. So my new vertex is going to be 0, 2. And that's because I had no h is 0, and we had no horizontal transformation. Also, because we had no horizontal translation, we are going to have our axis of symmetry be x equals 0. And then, of course, label a few additional points. The domain is still all real numbers. And our range will still start wherever our vertex is, the y-coordinate of the vertex. But now we are open down, which means our range will go down. So y will be less than or equal to the y-coordinate of the vertex, which is 2. Y equals 3 times the absolute value of x. This 3 here is telling me that I have a stretch of 3, or by a factor of 3. So I'm actually going to have to make a table of values for this one. So I can't just do horizontal or vertical transformations. So plugging in my normal parent function points for x, and then evaluating that in the function, plug in -3. 3 times the absolute value of -3 is positive 9. When I plug in -2, I get positive 6, positive 3, 0, 3, 6, 9. So our vertex did not change. Our vertex is still 0, 0. And then we have a -3, positive 9, -2, positive 6, -1, positive 3, and then all of its symmetrical points. Notice how there's symmetry across the axis of symmetry, 3 away, 3 away, 2 away, 2 away, and so forth. Connecting those points, we label at least 3 of them, including your vertex. And then, of course, our axis of symmetry did not move because we didn't shift left or right. So our axis of symmetry is still x equals 0. The domain is all real numbers. And the range will start at the y-coordinate of the vertex and go up because we are opening up. So it would be y greater than or equal to 0. Alright, so I want you guys just to use this as kind of a review, okay? So you are familiar with the different types of translations and what happens when those are applied to our parent function here. Please graph each function, state the vertex, the axis of symmetry, the domain, and the range.